We'll proceed on directional derivative along along a vector along an axis. If you see the programming concepts, then there is something that is always been a challenge in any of the programming area. That is generic program. Whatever I am doing, it should work for all the conditions. That is generic program. If I am writing an algorithm which would concatenate two lists, then it doesn't matter the list is map or list is a tuple or list is list array or it is a linked list. Doesn't matter. If I provide a function to concatenate two lists, then two list argument as a parameter to the function. I provide the feasibility. Then if someone passing the two list, then it would concatenate. Now person who is using my generic algorithm, now he can push map. Map means hash or dictionary, or he can push a linked list. He can push a vector, I mean array, vector. Array is different, vector is different in C++. And then like in Python, he can push tuple. Whatever he wants to, he can put string. Whatever he wants to can concatenate, if he believe that it is a list of items in any form, then he can just pass in and he get the concatenated. This is called generic program. If I am adding several items, then I have to find a way that will do the addition in generic fashion. Generic program. Generic programming has always been a tough challenge to either mathematician or a programmer. How I can write an algorithm that would work in all cases. Okay, there should not be two different things as far as the concept. If you like, if you writing a program, Python program, and you introduce one variable inside a function, you introduce one variable, okay, and then local variable, whatever it is, then do the work. Now introduce one more variable. Now there are two variables. Okay, if you see the complexity, what you have increased, complexity increases when you increase the number of variables in geometric fashion. Okay, GP, not in kind of addition. It will progress in the complexity in multiplication. So if you add one more, then it will be kind of, if it is 1, now the complexity is 1, then it will be 2. Now if you add one more, then it will be like, it will go even more. It will be 6. If you add one more, then it will be 24. So complexity start growing in geometrical progression. Not in, I believe, AP it is called something like that. So not in addition. It will progress in multiplication. So if you have one generic algorithm to concatenate the item, if you make a two cases, for this case, this is the concatenation algorithm. For this case, this is the concatenation. Then the complexity for the programmer who's using it grows exponentially or multiplication wise, whatever. So if I find a way to provide the addition, like if I say that I collect 10 orange per day, how many orange I have collected at the end of 5 days, then 10 plus 10 plus 10, then it becomes 50, or 10 into 5, it becomes 50. This is one of the way I can do the addition. But if someone says that the collection of orange is kind of dependent upon the day, so at the end of one day, the net collection of orange, okay, is 10. At the end of second day, any moment, the collection is different. Okay. Now a term called rate of collection per day. Like someone can say that rate of collection per day is day. Is day. Means at the end of half day, at that moment the rate of collection is half orange per day. At the end of one day, the rate of collection is one orange per day. If I say I am collecting 10 orange daily, means the collection is considered as 10 orange per day. So per day I am getting 10 oranges. Then at the end of 5 days I collect 50 oranges. What is the collection? Now collection is, now it is dependent upon the any moment. So if I say collection, what is the rate of collection at 2.5 days, the 2.5 orange per day? Or I can describe this example as person is collecting kilometer, he is walking. So if he is walking and at end of every hour I am seeing that he is walking 3 kilometers. So each hour he is collecting 3 kilometers. At the end of 10 hours he is collecting the 30 kilometers. Now the way, so he is walking at constant speed and every hour he is collecting 3 kilometers. No, he is not walking at constant speed. So he starts from rest and then he is increasing the speed slowly. Then what is its speed rate of collection is dependent upon the time. So when time is 2.5 hours, at that time if someone is checking his speed, then his speed is 2.5 kilometers per hour. Earlier 3 kilometers per hour was constant speed. Now at the end of at 4.5 hours, at that time if someone is checking his speed, then it is 4.5 kilometers per hour. At the end of, if I say he is working up to 5 hours only, then at the end of 5 hours, the his speed is 5 hours, 5 kilometers per hour. At the end of 2.2 hours, his speed is 2.2 kilometers per hour. How much is the total collection? Then you cannot do simple addition. Okay, if it is constant, then you can go for simple addition and multiplication. Okay, now someone wants to do, committed to do simple addition, then he has to make so many. What is addition? Addition, if you see graph wise, if I take a graph, then if speed is constant, then okay, so if I say in a graph there is a x-axis and there is a y-axis, there is x-axis and there is a y-axis. If x-axis is hour and y-axis is net collection per hour, how many kilometers he is collecting per hour? He is collecting 3 kilometers per hour. Then the y-axis there is a horizontal line that is 3 kilometers per hour. Now, if I make a rectangle for 5 kilometers, where width is 5 and height is 3, then 3 into 5 becomes area of the rectangle. That is the net addition. Now, he is from origin, he is starting and he is going like ramp. And then at every moment, the speed is whatever the time. If time is 3.5 hours, then his speed is 3.5 kilometers per hour. Then what is the net kilometer he has collected at the end of 5 hours? Now idea is that how we can calculate. When it is not smooth, we don't know at what time what is his speed, then we cannot add all the items. Not possible. I can multiply now. So now people they saw that if I calculate the area, if I have rate, if I have velocity vector, means if I have rate of change, that is kilometer per hour, if I draw against the r, kilometer per hour. If hour is the x-axis and kilometer per hour is y-axis, if I draw a graph, I get the area underneath, then it is the addition, simple. So if it is a triangle, then triangle means half of the rectangle. So if he is achieving 5 kilometers per hour at the end of 5 hours, then there is a rectangle of 5 of height 5. So the area of rectangle is 5 into 3. 5, 3, height is 3. He is achieving, okay, so at the end of 5 hours, he is achieving 5 kilometers per hour. So width is 5 and height is 5. So 5 into 5, then it is 25. So 25 is the net area of the rectangle. If there is a triangle ramp, then it is half of it. So 25 by 2, 12 and half kilometer he has collected. Now, the generic equation for doing the addition, if I have a rate of change and you want addition through generic way, quickly draw the graph. That's it. Quickly draw the graph and calculate the area, that is the addition. Now it is more generic to multiplication. It is more generic to simple doing the addition. Because now the variation in rate of change, if someone is saying every hour I am collecting every hour I am collecting 5 kilometers. Every hour I am collecting 5 kilometers. Then someone would say 5, 5, 5, at the end of 5 hours, 25 kilometers someone is collected. But someone would see it as rate of change also. Means the rate of change means kilometer per hour collection is 5 kilometer per hour. So he draw a graph of the velocity vector, that is 5 kilometer per hour. So 5 is the y-axis height, and then in horizontal axis it is 5 hour he is walking. Then 5 into 5, 25 kilometer he has walked. So whatever is the velocity vector or rate of change, then that becomes the y-axis, and whatever is the independent component, rate of change, whatever is the change, kilometer per hour, what is the hour, and draw the graph, you get the quickly you get the area and you get the net addition. So this is the integration is a funny way of doing the addition only, but it is generic. Now, whatever you want, just place in a algebraic equation of rate of change and then draw the algebraic equation against the independent component rate of change. If collection is that 10 mango per day I am collecting, the day is the independent component per day. Day is the independent component, and then 10 is the vertical, and just quickly calculate the area. Area is nothing but length into height as far as rectangle is concerned, and then quickly find the area and quickly find the addition. This is calculus. Calculus means this is integration, a funny way to calculate the net addition from the rate of change through the calculation of area. Now, directional derivative along a unit vector. Directional derivative along a unit vector. What is derivative? If I see dy by dx, if x is independent component and y is dependent component, then dy by dx, okay, if x is independent component, y is dependent component, then dy by dx, dy by dx is nothing but rate of change in y with respect to x. Okay, integration is if I have rate of change, if I draw a graph with independent component x and rate of change dy by dx, if I draw graph, if I calculate the area, I get the y. But in differentiation, if I have net collection y as the vertical component and horizontal component is the independent variable, then dy by dx rate of change I get. Okay, rate of change with respect to what? Dy by dx, rate of change in y with respect to x. Okay, now if I have a x-axis and y-axis, and if I have a graph in y-axis as per the x-axis, then if I calculate dy by dx rate of change at any moment, it is tangential at that point. This is what has been seen. If I have a graph of sinusoidal, at any moment, if I calculate dy by dx, if wave is like this at any point, then tangent at that point is dy by dx. So if I have any point on the graph, on the curve, and at that moment, if I calculate the derivative, then derivative is nothing but tangential line at that point. So if dy by dx is 0, if dy by dx is 0, means the tangent at that point is 0. If tangent at that point is 0, means the tangent is parallel. Parallel to what? Dy by dx. If we are differentiating with x-axis, differentiating with x-axis, and dy by dx is 0 at any point, the tangent is nothing but x-axis. The tangent is nothing but x-axis. Means the dy by dx is 0 at that point wherever it is 0. If that point is x0 or x0, y0, at that point if I draw the tangent is x-axis or parallel to x-axis. So if tangent gives a line, then it is parallel to x-axis. If tangent gives an vector, then that vector is same as I vector. So if I have a function y fx on x, then dy by dx is tangent at that point. If dy by dx is 0 at some point, then tangent at that point is parallel to the independent variable axis through which we are calculating the dy by dx. So now, but what is the constraint here? Constraint here is that we have only one independent variable through which I can calculate the dy by dx. This is not generic. Integration itself is not, or differentiation itself is not generic. Why it's not generic? It's generic, right? It means dy, if I have one independent component x and dy by dx is 0 at that point, if it is a tangent, then it is parallel to x-axis. If I see the curve, if it is parallel to x-axis, then that point, it is a extreme point, minima or maximum. Okay, now I know if I need to calculate minima or maxima, then at that point where I'm thinking the curve is a kind of the curve is a, in a situation their tangent is parallel to the x-axis. That point is minima or maximum. Like curve is coming like this and then it is going like this. So here, so if it is coming like this, then tangent at any point is like this. But at here, when it is turning, the tangent is parallel to x-axis, and then tangent slope is then positive. Slope is negative, and then slope is positive. Now, very nice. Now, my question, only one question is, so I'm able to find maxima or minima with respect to x-axis. This we have never seen. With respect to an independent variable x. So x is an axis with respect to independent variable x. I am able to calculate maxima or minima by calculating dy by dx equal to 0 and then trying to get the x0 value for which dy by dx is 0. At that x0, it is hitting the curve. There it is maxima or minima, because if it dy by dx is 0, means their tangent will be parallel to x. What about y? Y is a function, right? Y is a function over x. Now, what about minima or maxima in y with respect to any artificial line? Minima or maxima in y with respect to a line that is x-axis, that is dy by dx. If there is a line, the equation of the line is g, not x, g. Okay, then what is the maximum and minimum in y that is seen with respect to g, not x? G can be x, that is one corner case, but G can be different. Like there is a line that is y equal to 3 minus x. There is a line that is y equal to 3 minus x. If this is x axis, this is y axis, then line passes like this. If x is 3, then y is 0. If x is 0, y is 3, then this is the line. If I have a equation in y, then that curve would be maximum or minimum with respect to this line, not this line. This is x-axis. I calculate dy by dx. If this line is equation of the line is, I call it gx. Gx. Okay, the equation of y is fx. There is another equation of a line that is gx. Then What is df by dg? What is df by dg? What is variation that is seen in y with respect to this line, not x-axis? If we calculate dy by dx, then we see that the change in y when we do unit change along x-axis. If I do unit change along new line, that is gx, along the gx, if I do unit change, then how much change I see along y? So if I have a point on G, that point name is U has some x and y. If the point is U, at this point, if I have y value, since it is x0, y0, there is a point there. So if there is a y value, if I move along the line delta U, there is a y value. What is delta y by delta U? If U is there is a line gx, that is x plus y equal to 3, and there is one point called x0, y0, there is another point called x2, y2. Then at x2, y2, what is y? x0, y0, what is y? Delta y, subtract delta y, and u and another x0, y0 and x2, y2. If x0, y0 is u and x2, y2 is delta u from the u, then if I see delta y vertical change, then along the line there is change, that is delta u. What is delta y by delta u? This is directional derivative of a function, that is fx y, along the line or vector, that is g. Earlier we were calculating dy by dx. Okay, that is directional derivative of y along a line vector I axis, or line x axis, that is y equal to 0. So that is dy by dx. Now if I have any hypothetical line, and in hypothetical line if I have 2 points, one is u and one is u plus delta u, then if I get the y, then there is a delta y change. Then what is delta y by delta u? Directional derivative of a function fx with respect to any imaginary line or vector g, df by dg. This is directional derivative of a function with respect to any vector g or u, dy by dg, dy by du. If I have two independent components, three dimensions, now instead of x-axis, I have xy plane, x-axis, y-axis, and z-axis. Now, if I have xy plane, and if the dependent component is z, independent component is x, comma y, then what is dz by du? Okay, what is u here is, okay, so what we were calculating is there can be two derivative here, dz by dx. This is called partial derivative. dz by dx, the z variation, vertical side where delta z variation, that is seen if I vary one unit of component along x-axis, dz by d. Now, if I vary one component along y-axis, then dz by dy, dz by dx, dz by dy. So, x-axis is a I vector, y-axis is j vector. If there is any other vector u, I vector, j vector, they are unit vector. If there is another unit vector u on the xy plane, then what is dz by d? If I can calculate dz by dx, if I can calculate dz by dy, then what is dz by d? This is directional derivative of a graph, that is z, along any unit vector u. Okay, now derivative is complete. Derivative cannot be only along x-axis, y-axis. Derivative must be along any axis. Now it is generic. But how we can calculate? There is no fixed way to calculate the derivative along any axis. We have done something in this area, and probably we will try to file whatever, either disclosure and later on what we can see, that is derivative along any vector as far as constraint. So now this much, so if you want to find the derivative of a function along any vector, then typically that what we have seen in the past, then in that case, if I have a function fxy and if I have a vector u, then df by du is nothing but gradient vector of f dot product of unit vector u. If I calculate gradient vector of f, and if I do dot product with u unit vector, then it becomes dz by du. This is what we have already seen. Okay. Now, what is more required here? Now, there is something called constrainment. Constrainment in a sense that if I have a xy plane, then against each x comma y, against each x comma y, I have z value. Similarly, against each x comma y, then I have maximization and minimization calculation. So if I have against each x comma y on xy plane, if it is any x comma y on xy plane, then it is called unconstrained region. If it is unconstrained region, means I am taking complete xy plane. If that is the case, then it is unconstrained region. In unconstrained region, I have z value fxy for any x comma y. But if I take constraint region in the sense, in the xy plane, I have taken a circle. Now I want all the calculation inside the circle and including its boundary, not beyond that. This is the new world. So you have to calculate all the fxy, all the vertical z only in this circle. This is called constrainment. Now if I have a constrained circle or constrained line, I draw a line and below the line or on the line only I have to take all the xy value, not above. So this is called constrained calculus. Constrained calculus where the independent component in xy plane is constrained to a set of value. You cannot take x and y anyone anywhere you want. Like if I am calculating global maxima and global minima. If I have global maxima and global minima, then I can say in full xy plane, I have this point as maxima and this point as minima. It is global minima because it is the lowest point on all the local minima. If it is a global maxima, it is maximum on all the local maxima. If that is the case, now if I have a constrained region on the xy plane, then global minima and global maxima must be inside the region including its boundary. Beyond that, there is ocean, there is nothing. Okay, or I can say there is null, nothing. So if I take a circle, that is called closed region. Closed region, if I am taking a closed region, then inside xy point will be taken in the closed region only. If I draw a line and then closed region is on the line and below the line, if like I say x plus y less than equal to 3, if I say x plus y less than equal to 3, then I am drawing a line and on the line and below the line only I have to take set of x and y point, and there I have to calculate maxima or minima in that region, closed region only, global maxima or global minima. Now in this region, now if I have a constrained region, then in constraint region, if I want to calculate maxima or minima, then Lagrange is a way, means there is some Mr. Lagrange, he comes into the picture and he talks about that how I can calculate constraint maxima or minima. This is what we have already seen. So if I have a line x plus y less than equal to 3, then in this constraint region, how I can calculate maxima or minima. So Mr. Lagrange is saying that if I have a function fxy equal to something, like we had taken example of a company, and company has a production. In that production, production is a function fxy, then fxy is x to the power 2 by 3, y to the power 1 by 3, where x and y are two raw materials. So x is number of the raw material, y is the number of another raw material. The production is x to the power 2 by 3, y to the power 1 by 3. How production will be maximum? Provided there is a constraint that number of x plus number of y item should be less than equal to c. That is a constraint. So if I draw x plus y less than equal to c a line, then x and y must be fall on the line or below it. Otherwise, x to the power 2 by 3, y to the power 1 by 3 will be maximum when both are infinite. So production has to be with the raw material x and y. Their count must be on the line of the constraint C or below it. Then Lagrange is saying that if I draw contour for a fixed f, if I draw a set of x and y in the xy plane, if I draw a contour, then that contour, all the contour points must be below the kind of wherever I am thinking about minima and maxima, at least those minima and maxima points must be on the line of the constraint line or below it. So keep drawing the contour. Now if f is 1, then what is the contour diagram? If f is 2, contour diagram is what is the set of x and y that through which I have f equal to 1. So keep growing the f, and then one time you will hit the constrained line. If you go beyond it, then you have crossed the constraint. So maximization in f would appear when f is touching the constraint line. If f is touching fxy equal to x to the power 2 by 3, y to the power 1 by 3. If f is touching the constraint line, means wherever it is touching the constraint line is tangential to the function f. If that is true, if it is tangential to function f, then gradient of f is perpendicular to the tangent, and gradient of tangent itself is perpendicular to the tangent itself. So they are parallel to each other. Then we can say that gradient of f equal to lambda gradient of g. If g is the constraint line and f is the production line, production curve, then gradient of f, because if I draw gradient at any point, it is radial. Means at that point, if I draw tangent, then it will be perpendicular. We have talked detail in the last video. So now if we continue like this, then both gradient, tangent's gradient means the constraint line's gradient at point x0, y0 where curve is touching it. There the gradient and the curve gradient both are parallel to each other. So gradient of f equal to Lagrange multiplier, that is lambda gradient of g. Now we took example where fxy equal to x to the power 2 by 3 and y to the power 1 by 3. This is the production function. If production has to be maximum, then then I have to follow one constraint. Constraint is number of the price of the x item and price of the y item. Net input price should be less than c, less than equal to c. C is the constraint. So if the number of x item is p and number of y item raw material is q, then p into x plus q into y less than equal to c. If I keep p and q as 1, means they are at $1 or 1 cent per item less than equal to c. If I keep c as 3, then it becomes x plus y less than equal to 3. This is what we are taking, x plus y less than equal to 3. If this is the constraint, then our constraint function gxy is x plus y, whereas fx is x to the power 2 by 3 and y to the power 1 by 3. So gradient of fx should be lambda into gradient of gx. So gradient vector of fx will become 2 by 3 x to the power minus 1 by 3 y to the power 1 by 3 I plus 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3 equal to lambda, and x plus y less than equal to 3, the gradient vector will be I plus j. Now if I put it, then lambda I plus lambda j is on the right side. Now lambda becomes the x component here, lambda and lambda I, and here I, then lambda j and here j. Now x component, y component with lambda if I equate, then it becomes 2 by 3 x to the power minus 1 by 3 y to the power 1 by 3 equal to 1 by 3 x to the power 2 by 3 y to the power minus 1 by 3. If I calculate this, I get x equal to 2y. Now, if I put x equal to 2y into the equation, then it becomes x plus y equal to 3, then 3y equal to 3, y equal to 1, and x equal to 2. So, at x equal to 2 and y equal to 1 on the constraint line, I can see maximum f value. That is 2 to the power 2 by 3 into, okay, 2 to the power 2 by 3 into 1 to the power 1 by 3. That is the maximum value f would attain, provided there is a constraint line x plus y less than equal to 3. Or there can be another local maxima minima that we can calculate by df by dx equal to 0, df by dy equal to 0. That comes as x and y equal to 0, 0. There it is, certainly it is not maxima. So maxima we have found through Lagrange. Now, can we use, the question arises that can we use our directional derivative concept here? What we are trying to achieve? If I have a curve and if I have a line, then we are trying to find curve is touching a line. So line is becoming tangent to curve where it is touching. So tangent is parallel or the line is. Now if line is gx and curve is fx, then df by dg should be 0. If I get that xy point, at that point the curve and the line is tangent to the curve. So we forget the x-axis. If I say, if I have a curve, curvature surface, if surface is there, that is fxy, then dfx by dx. If I calculate dfx by dx and I set it to 0, then in xz plane, I say that wherever I am finding dfx by or dz by dx as 0, at that point, if I draw a tangent, tangent is parallel to x-axis. If I do dz by dy equal to 0, at that point, if I draw the tangent, that the tangent is parallel to y-axis. If I do dz by dy equal to 0, dz by dx equal to 0, I come to a point x0, y0. So at that point, if I draw a tangential surface, because the surface is 3D, then that surface is parallel to xy plane. So I can say df by dx comma y. Df by dx comma y means derivative of function fxy with respect to xy plane should be 0. If that is the case, then there the tangential surface is parallel to xy plane. Now, if I am saying if I have a surface fxy and surface at some point it is touching a particular another surface, that surface equation is gxy and surface equation is fxy. If fxy is a curve, it is a curved surface, and fxy, when at some point if I draw a tangent, that tangent is parallel to some other surface, then that surface, if I derive f with that surface, then it is 0. If I have a surface equation fxy, if I derive fxy with respect to xy plane, and then I get a tangential surface. If I have a surface fxy and at any point if I do derivative of fxy with respect to xy plane, not through a line, xy plane, dfxy by dx comma y, derivative of fx with respect to xy plane. So at any moment, if I calculate the derivative, then it is a tangential surface at that point. If that is true, if dfxy by dxy equal to 0, means tangential surface is parallel to the xy plane. dfx by dxy, differentiation in fx with respect to xy plane. If it is 0 at any point x0, y0, then if I draw tangential surface at x0, y0, then that surface is parallel to the xy plane through which we are calculating the derivative, the denominator. If I say my fx is x is a is a is a is a surface, and at any point x0 y0 I can calculate a tangential surface. If tangential surface is parallel to a particular surface, it means if I derive this function with respect to that surface, then if I set it to 0, if I set it to 0 and calculate x comma y x0 y0, at x0 y0, if I draw a tangent on the surface, the tangent is nothing but tangential surface is nothing but parallel to the surface through which I did the derivation. This is the invention that is going through us. So this is directional derivative of function fxy with respect to any surface. If when we were calculating maximum and minimum, we were doing partial derivative or indirectly directional derivative of a surface with respect to xy plane. If it is 0 at some point, then at that point if I draw a tangential surface that is parallel to the xy plane, because we did the directional derivative along xy plane. If I do directional derivative of a surface with another surface than xy plane, and then if I set that derivative to 0, then I tend to calculate x0 y0 z0 point. At that point on the tangent on the surface, if I draw a tangential surface, then that tangential surface will be parallel to the surface through which I did the directional derivative. So if that surface equation is gxy, and if I am calculating dfxy by dgxy, directional derivative of a surface fxy with respect to another surface gxy, then if I set it to 0, df by ddx, df by dt, if I set it to 0, then whatever x0 y0 point I get in fxy where I did dfx by dg equal to 0, at that point, if I draw a tangential surface on the fxy surface, that tangential surface will be parallel to the surface on which I calculated the directional derivative. Similar to if I do dfx by dx comma y, directional derivative of the surface with respect to xy plane, then if I get x0 y0 point where this directional derivative is 0, at that point if I calculate the tangential surface, that surface is parallel to the xy plane. Similarly, if I have a surface and if I do the surface directional derivative along another surface fx dfxy by dgxy, then if I set it to 0, I get a point x0 y0. There if I draw a tangential surface will be parallel to the surface through which I did the directional derivative along. Okay, so that is the concept. Now we will go back to our production unit. Now production unit function is fxy equal to x to the power 2 by 3, y to the power 1 by 3. Now I want this fxy to be maximum, to calculate the maximum with respect to another line, that is x plus y equal to 3. I want maxima or minima in fxy with respect to gxy, not xx. So I don't want df by dx. I don't want df by dy. I want df by dg. dxy is a constraint line, that is x plus y equal to 3. df by dd, if I set it to 0, then I get to have x0, y0 point. At that point, this fxy curve, if I calculate the tangent, that is nothing but this is gxy. This is what we are looking that I was trying to find a point at which the fxy curve would touch the constraint line, means it would be tangent. df by dg should be 0. No need of the Lagrange lambda and so many calculations. Then you find relationship between x and y through Lagrange, and then you go ahead and place that xy relationship in the constraint function, calculate x and y value, then set fxy and see it is maximum. Here, directly calculate df by dg and set it to 0. Quickly get the xy value immediately. Okay, we'll try now. So, if I have constraint function x plus y equal to 3, then I'll change it to a constraint vector. So, I'll calculate dy by dx. So, dy by dx is minus 1. So constraint vector is I minus j. Now constraint vector is suppose if gxy is a constraint line, then g is a constraint vector, then I minus j. Now dfy dg, the directional derivative of function f along the constraint vector, not the line. That is directional derivative of a function along unit vector u. So if I want to calculate df by dt, the gradient of f dot product of unit vector g. Now gradient of f is 2 by 3 x to the power 2 by 3 x to the power minus 1 by 3 y to the power 1 by 3 I plus 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3 j dot I minus j. Then if I take equal to 0, that I have to set now. Then if I take left and right, then left will be 2 by 3 x to the power minus 1 by 3 y to the power 1 by 3 equal to 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3. If I do here and there, it becomes 2y equal to x. Okay, it becomes, okay, so it becomes 2y equal to x. Now, if I place, sometime it gives value also, that we will see. 2y equal to x. Now, we have x plus y equal to 3 in the line. So, y equal to 3 minus x, or x equal to 3 minus y. Here, x equal to 3x equal to 2y. So x I'll replace with 3 minus y. So it becomes 3 equal to 3y, y equal to 1 immediately. No need to have any lambda in between. Quickly. Okay, df by dg, g is a vector. Then we quickly find that it is x equal to 2y, where x equal to 3 minus y. So y equal to 1, x equal to 2. Okay, this we have seen the maximization in production function fxy with respect to constraint vector gxy, that is x plus y less than equal to 3. Quickly we get. No need to have lambda and so many things, gradient vector or something like that. Now let's see another example. Now the gxy, that is the closed region, constrained region, is x square plus y square equal to 2 square. X square plus y square equal to 2 square. That is the constrained circle. Now the production function fxy equal to x plus y. Now if I want maximization in x plus y with respect to the closed region, that is x square plus y square equal to 2 square. So we want if gxy is x square plus y square equal to 2 square, where fxy is x plus y. If that is the case, then df by dg unit vector E is gradient of f dot product unit vector of g. Now gradient of f here is I plus j. X plus y means I plus j, and that side equation is x square plus y square equal to 2 square. So y equal to 4 minus x square square root dy by dx, because we are turning into vector. So dy by dx is 1 by 2 minus 2. So minus x by square root of 4 minus x square. Now the vector of g is I minus x by square root of 4 minus x square. Now if I do multiplication of gradient vector of f and g, then it would turn up as 1 minus x by square root of 4 minus x square equal to z equal to 0. If I take this side and settle it, then it becomes x square equal to 4 minus x square, that is x square equal to 2. X equal to square root plus minus square root of 2. Immediate. X equal to plus minus square root of 2. If I place there x square plus y square equal to 4, then y equal to plus minus square root of 2. Now I have 2 points where it is x square plus 2 square, that is the constraint closed region. Square root of 2 comma square root of 2 and square root of 2 minus square root of 2 comma minus square root of 2. This is x and y value where there are extrema with respect to constrained region, not with respect to x and y or xy plane. Then if I see x plus y is a line, that is production, that is fxy, and gxy is a circle, then at 2 points it would touch each other, where one is maxima, that is square root of 2 comma square root of 2, and one is minima, that is minus square root of 2 minus square root of 2. Now let's take another example. Another example, now the production function fxy equal to x square plus y square, whereas the constraint function gxy is x square plus y square less than equal to 45. Okay, now this is the equation. Now the production function x square plus y square we will make even more complex. X minus 1 whole square plus y minus 2 whole square. Production function is x minus 1 whole square plus y minus 2 whole square. This is a paraboloid where the minimum of the paraboloid is 1 comma 2. So this is a paraboloid, parabola, and then paraboloid where the minimum point touches the xy plane at 1 comma 2. X minus 1 whole square plus y minus 2 whole square. And there is a region, closed region, constraint region, x square plus y square less than equal to 45. Now tell me where this paraboloid would achieve maxima when xy point I am confined to take from a constraint function x square plus y square less than equal to 45. So fxy, the production function, is x minus 1 whole square plus y minus 2 whole square, whereas x and y points, set of points what we'll take to draw this paraboloid must come from a constraint function, that is x square plus y square less than equal to 45. If that is the case, now let's calculate the gradient of f. So gradient of f is 2 into x minus 1 I plus 2 into y minus 2 j. Now let's do vectorization of gxy. So vectorization of gxy means y equal to 45 minus x square root. Okay. Now dy by dx, if we calculate, then it will come as minus x by square root of 45 minus x square. Now if I do gradient of dg by df by dg equal to 0, okay, then directional derivative of function f along g vector, that I have to set it to 0. That is gradient vector of f dot product of unit vector of g, that is the result that I have to set it to 0. So 2x minus 1, 2x minus 1 into 1. So what is the vector form of gxy? I minus x by square root of 45 minus x square j. X I have taken component of the vector as 1. That's why we are calculating dy by dx. Then 1I minus dy by dx, x by square root of 45 minus x square y. Now if I multiply this, then it becomes x 2 in braces x minus 1 minus 2 y minus 2 multiplied by x divided by square root of 45 minus x square. If I take this side and that side, then 2 I can cut down, then it becomes x, then it becomes x minus 1, x minus 1 equal to y minus 2 multiplied by x divided by square root of 45 minus x square. Now if I take this side and that side, it becomes x minus 1 multiplied by a square root of 45 minus x square equal to y minus 2 into x. If that is true, then if I do the square of these two regions, then it becomes x minus 1 whole square into 45 minus x square equal to y minus 2 whole square x square. Okay. Now if I see the equation x square plus y square equal to 45, then y square I can or x square, then x square equal to 45 minus y square. Okay, now I have here x minus 1 whole square, 45 minus x square. The x square will change to 45 minus y square. Then 45 would cut down, then it becomes y square. Then x minus 1 whole square, then 40, then y square, x minus 1 whole square, y square equal to y minus 2 whole square x square. Here I have changed x to y. So this is something I have changed 45 minus x square. 45 minus x square. Or if I remove the squares everywhere, I mean it's complex in calculation through the speech. So x minus 1 into a square root of 45 minus x square equal to y minus 2 into x. This we are getting. Now x square equal to 45 minus y square. Now if I place here 45 minus x square, the x square is 45 minus y square, then it turns up as square root of y square. Then it is y. Now I have x minus 1 into y equal to y minus 2 into x. Okay, now x minus 1 into y is nothing but xy minus y, and that side y minus 2 into x is nothing but x minus y minus 2x, x into y minus 2x. Here x into y minus y. So xy would go. So y equal to 2x. This is what I believe so. Okay, this side x minus 1 into y. So xy minus y. That side y minus 2 into x. xy minus 2x. Then it becomes y equal to 2x. Y equal to 2x. Now if I set there x square, now y square plus x square. So y equal to 2x, y equal to 2x, y square plus x square. Okay, then it would turn up as 4x square plus 5 plus x square. 5x square equal to 45, x square equal to 9. So x equal to plus minus 3. If that is true, then y equal to plus minus 6. Now quickly, miss, through speech if we can do, then paper it is kind of 10 seconds. So df by dg, the directional derivative of function f along any vector g, if I try to find the maximum and minimum point x0, y0, then at that point if I draw a tangent, that is the g, that is the directional derivative. If I calculate directional derivative of f along a vector g, then if I set it to 0, I'll get a point x0, y0. At that point along f, if I draw a tangent, that tangent is nothing but parallel to gx. This is what we want. The gx, the constrained vector, must be touching the fxy. That point I want. Through reverse way, we calculated it happened when we calculate the directional derivative of function f with respect to vector g. And if I set it to 0, I get the touching point where g is tangent to the f. Now, if I have df by xy plane and the point where I get this value as 0, at that point xy plane is touching the fxy. If I calculate df by d0 and set it to 0, I get a point. If that point, if I draw a tangent, the tangent, if I have dxy vector surface, it will touch the tangent. It will touch the fxy. So the constrained maxima or minima we can calculate, not required that we calculate through Lagrange way. The constrainment we can calculate through the directional derivative of a surface, directional derivative of a function, any function, 2D function, 3D function, 4D function, any function along a unit vector, along a line, unit vector along a surface, whatever. If I set it to 0, that unit vector, I get the set of points. At that point, the production function would touch the constraint line. This is what we are looking. So maximization, minimization in a function can be achieved when we calculate directional derivative of that function along the constrained function. And then if I set it to 0 and try to get the x0, y0 value, that value is the maximum or minimum in the production function curve fxy. So now the derivative is generic. Derivative against x-axis, derivative along y-axis, that is called partial derivative, or derivative against a surface x and y. Now, if we have derivative against any surface, then we can, if that surface, derivative against any surface, if I consider that surface as a constraint surface, then we have constraint maxima and minima with the directional derivative along any vector. So this is the real life or industry based usage of directional derivative as far as conditional maximization and minimization. The maximization, minimization of a particular graph within a particular closed region, if I want to calculate, that we can do. And this is our invention. Now, the derivative, the generic derivative is not along x-axis, generic derivative is not along y-axis, generic derivative is not along the xy plane, the generic derivative of any curve is along any surface, any line. That is the directional derivative along a particular vector. It has usage in the finding the maximum minimization along inside any closed region or any closed interval or any kind of constrained region. Amazing, right? So this is the invention that we will find disclosure or patent. Okay, so this is kind of we have finished, and if someone can work on the more example of getting the maxima and minima with the constraint dxy, then he can do. Okay, so now it's time that we will see more in the calculus, probably line integral, flux integral, and curl integral. So many things are in the plate that we will see.